As we have already discussed, this lecture series about communication systems. In communication systems, the first topic we are going to start with is noise. In order to analyze noise, we need to understand the basics of probability and statistical processes. So let us start understanding the basics of probability. We will understand it to a level so that we will be comfortable to deal with communication systems and especially the noise part of communication systems. So let's start with the basics of probability. In the basics of probability, the first topic that we will be covering is axioms, or we can say the properties of probability. So let's see the axioms of probability. These are simple statements which we might have already studied in the previous classes, but let's revise it and have a little bit of insight into the axioms or properties of the probability. So the first axiom when it comes to probability is simply defining the range of probability of any event. Say for example, the event is represented by symbol A. Then the probability of occurrence of that event A is actually given by P of A. So the range of the probability of A is given by the probability of A is actually lying between 0 and 1. The minimum value of probability of any event A is given by 0 and the maximum value of probability of any event is simply 1. The probability lies between 0 and 1. The second property or axiom is probability of A union B. Here the symbol, it is called as union. We can also call it as OR. Sometimes we will also call it as either or. All of the three names will be representing the same thing. That is usually in the case of Venn diagrams, and in the case of set theory we call that as union. So let's use the word union here. The probability of A union B, or we can say the probability of A or B, is simply given by P of A plus P of B minus P of A intersection B. Here the third symbol, the third term, intersection. Here I intersection, instead of union we may call this symbol as intersection. We may call, instead of or that we have used for the other symbol, here in this case for this symbol we can use the word and. So here this term P of A intersection B, or P of A and B, the third term P of A intersection B, it is actually giving the joint probability. Let me give a little bit of a definition for this joint probability. So joint probability is actually the probability at which both the events together they occur. That means A and B are two events which we have named them, two events are there which we have named them as A and B, and the joint probability is actually given by P of A intersection B, or the probability of occurrence of A and B together is called as the joint probability. And P of A and P of B are individual probabilities of those events, and now P of A union B, or P of A or B, is actually given by P of A plus P of B minus P of A intersection B. This is the second probability, second axiom or second property. When it comes to the third property, we can simply it is actually given by P of A1 union P of A2 union P of A3, so on up to AN, is given by probability of A1 plus probability of A2 plus probability of A3, and so on up to probability of AN. Here this property holds good only under one circumstance. That circumstance, or that condition for this probability equation to hold good, is that mutually exclusiveness. So mutually exclusiveness in the sense, it means using the plain English we can say that if some events A and B, say for example A and B are there and these events are mutually exclusive, it means that if A occur then B doesn't occur, if B occur then A doesn't occur. It means that both will never occur together and the chance of occurrence of both together is simply zero. So in terms of the set theory I can write it like this. Say for example P of A intersection B is equal to 0, or we can say P of A and B is equal to 0. It indicates that probability of occurrence of A and B together is simply 0. In such a case, the probability of occurrence of P of A union B, or the probability of occurrence of P A or B is equal to P of A plus P of B, the probability of A added to probability of B. If we see the earlier equation, the second axiom which we have given earlier, for the second axiom here, the second axiom equation, if we are putting this term that P of A intersection B, if this term is simply 0, then P of A union B is equal to P of A plus P of B. This, whenever this property is satisfying, this is called as mutually exclusiveness, and in such a case of mutually exclusiveness this third property is holds good. Actually the definition of mutual exclusiveness we have seen for two events P of A union B. If the same is extended to various events A1 to AN, then the property will be turning up in this manner. Probability of A1 union A2 union and so on up to AN is simply given by probability of A1 plus probability of A2 plus probability A3 and so on up to P of AN. So these three properties, and from the third property we can also give another statement, but let me explain you that also. Say for example, let me put some another symbol for this as a fourth property. It is actually a consequence of the third property itself, but we will learn it as a fourth property. Suppose there is one sample space. Sample space is combination of various events. So this one is the sample space. Let us give it diagrammatically as combination of many events in this way: A1, A2, A3, A4, A5, A6, A7, A8. So in this sample space there are 8 events and there is no other event outside of this sample space. All the events which we have taken A1 to up to A8 are inside the sample space itself. In such a case we can say P of S is equal to 1. The reason 1 is coming here is the probability of sample space is simply 1. We have already discussed from the first axiom. If we say the probability of any event is simply lying between 0 and 1, but if the event itself is the sample space, then the probability is simply 1. The reason is if any event is considered, then that is a part of this sample space. That is the reason probability of sample space is equal to 1. If we go deep into this relation, or if you go further one step deeper, in such a case I may write this one like this: P of A1 union P of A2 union P of A3 up to A8 is equal to. So let us understand what we will get toward the right side of this equation. So P of A1 union A2 union A3 and so on up to 8 is simply the probability of sample space itself, because A1, A2, A3, A4 all of them put together are becoming the sample, the total sample space. So this is simply P of S, and we know that the probability of sample space is simply 1 because all the events are contained by the sample space and there is no other event outside the sample space that will be occurring. So in such a case the probability of all the events together is simply given by the probability of sample space itself, and that is simply given by A1, simply given by 1. So now here in another, if we go another one step deeper, we can see that here A1, A2, A3, A8, all these events are satisfying one property. What is that property? We have discussed it in the third axiom. That property is mutually exclusiveness. The reason is I will explain now. They are mutually exclusive because the probability of joint occurrence of any two events out of this A1 up to A8 is simply 0, because from the sample space itself we can understand that the probability of occurrence of the probability of joint occurrence of any two events out of these events from A1 to A8 is simply 0. So from this, if we apply the definition of mutually exclusiveness in this fourth axiom, we will simply understand that, or we will simply deduce that, since the probability of joint occurrence of any two events is simply 0, the probability of occurrence of union of all the events is the probability of occurrence of, the sum of probability of occurrence of from A1 to A8, events from A1 to A8, or simply we can say probability of A1 plus probability of A2 and so on up to probability of A8. Since all the probabilities are added, we will be getting 1. The reason is that all the probabilities are added, then all the events are added, we are going to get the sample space. In such a case, all the probabilities are added, we will be getting simply 1, and that 1 is simply again probability of the sample space, yes. So these are the 4 basic properties of probability theory. Now we will be going a little bit one step further. We will be understanding the definitions, we will be understanding, or we will be discussing the definitions of some important terms, say like joint probability, conditional probability, Bayes theorem, total probability, and application of Bayes theorem. So let's move further to the next slide. So now let us start with the definition of joint probability. Joint probability is, we have already discussed this one when we are discussing about the second property of probability, where we have told that P of A union B is equal to P of A plus P of B minus P of A intersection B. There the third term P of A intersection B, or in another, in the normal English we call it as A and B. The probability of A and B is actually called as the joint probability. So it signifies that this particular quantity, probability of A and B, will be actually giving us the probability of occurrence of A and B together. So A and B together is called as joint probability. So sometimes there are two events, there is a chance of occurrence of both of them together. In such a case, it's called as a joint probability. It is actually mathematically given by probability of A intersection B, or probability of A and B. This is called as the joint probability. The second term that we are going to understand is conditional probability. Conditional probability is simply given by P of A by B, or P of B by A. So here A and B are two events, and the conditional probability P of A by B is simply given by the probability of occurrence. Let me write here the definition. Here we need to write probability of occurrence of event A, or I am simply calling it as A, given that event B has or is already occurred. So here it is indicating the probability of occurrence of A, but it is also indicating that B is already occurred. That means it is giving us the probability of occurrence of A given B has already been occurred. So in such a case we call it as conditional probability. Simply again, P of B by A is the probability of occurrence of B given A has already been occurred. Such a probability is called as P of A B by A. Now let us express the conditional probability P of A by B, or P of B by A, in terms of joint probability. So in this expression of conditional probability in terms of joint probability will be useful for us in further analysis of probability concepts, which will be used in communication systems. So let me give the expression of conditional probability in terms of joint probability. So conditional probability P of A by B, which is actually giving us the probability of occurrence of A, given that already that event B has already been occurred, is actually given by P of A intersection B divided by P of B. Here the numerator term I have already told you. P of A intersection B is the probability of occurrence of A and B together. A and B together. The probability of occurrence of A and B together is actually given by P of A intersection B, and P of B simply the probability of occurrence of B. So in this way the conditional probability P of A by B is given in terms of expression for joint probability of A and B. So now let us see. Similarly, we can say the other one P of B by A is simply given by P of B intersection A whole divided by P of A. Now let us see the statement of Bayes theorem. Bayes theorem is having one statement. Here Bayes theorem is expressing the probability of occurrence of A by B, or the probability of occurrence of event A given B has already been occurred in terms of P of B by A. That means the occurrence of probability of A given B has already been occurred is given in terms of probability of B given A has already been occurred. So this reversal of terms whenever the expression is involving both the conditional probabilities, then that expression, that statement which is actually forming that expression is called as a Bayes theorem. So now let me put down the expression. P of A by B is equal to P of B by A into P of A divided by P of B. So this is actually the statement of Bayes theorem. Now let us go to express the other one. The other one is simply P of B by A. P of B by A is equal to P of A by B into P of B whole divided by P of A. These expressions, the expression of one conditional probability in terms of the other conditional probabilities, are used for further analysis of our probability concepts, which will be used in our communication systems. So overall this is called as the Bayes theorem. So the expression of one probability, conditional probability, in terms of other conditional probability is called the Bayes theorem. Now let us go further deep. What is called as, let us go into the concept of total probability. Here total probability is simply can be given as, say for example there is one event B, and this event is composed of various other events which are also having some other parts in themselves. That means I can better explain you using a Venn diagram. Here let us consider this Venn diagram again. In this Venn diagram there are various events like this: A1, A2, A3, A4 and A5. Now there is some other event called as B, which is actually given by this circular shape. This called, I am naming it as B. Now this B, from the Venn diagram we can say that B is actually comprising of three events. B is comprising of three events. Let this arrow indicate that B is comprising of some other events: A2, A3, A5. But again this B can be written as B intersection A2 or B intersection A3 or B intersection A5. Here A2, A3, A5 are three events, and B is having some part of B is divided among A2, A3, A5, and A2, A3, A5 are also events by themselves, which are having some parts which are not covered by B. Say these parts are not part of B. So such a diagram here, it is indicating that B is having three events in itself, A2, A3, A5, which are having some other parts which are not a part of B. So in such a case, we can say that B is the intersection of B itself is having the intersections with A2, A3, A5. This I can represent like this. So now here, if we understand this part, so this part P of A intersection A2, sorry, B of A intersection A2. So this part, particular part, let me give it by, let me give some other color for this. So let me use this red color. So here, this part, this dotted part here, it is simply B of B intersection A2, and this other the top part, I will put the longitudinal lines here. Here it is P of B intersection A3, and the right side part, let me put some slant line here. So this is actually the B intersection A5. If we observe, these three parts are also mutually exclusive. We have already given the definition of mutually exclusive. There is no common part between those two things, then that is called as the mutually exclusive. So here we observe that these three parts are also mutually exclusive. If such a case is there, then I can simply write it as probability of occurrence of B is equal to probability of occurrence of B intersection A2 plus B of probability of intersection of B intersection A3 plus probability of occurrence of B intersection A5. In such a case, we can see here, because these three events, B intersection A2, B intersection A3, and B intersection A5, are not having any common part, so we can in order to get the probability of occurrence of B, we can simply add the probability of occurrence of these three parts. So in this way, the probability of occurrence of one event is actually given by sum of probability of occurrence of the underlying events. So now if we apply Bayes theorem here using conditional probabilities, not only application of Bayes theorem, we will see that later. First of all, we will apply the expression for conditional probability here. The expression for conditional probability, earlier we have seen the expression for conditional probability in terms of joint probability. So these expressions, we shall apply these expressions here in this big expression. We can simply write this P of B intersection A2 as P of B divided by A2 into P of A2 plus P of B divided by A3 into P of A3 plus P of B divided by A5 into P of A5. Because we know that P of A divided by B divided by A2 is simply P of B intersection A2 divided by P of A2. Then P of B2, P of A2 will be getting cancelled. After that, we will be only remaining with P of B intersection A2. So in this way, using the joint probabilities expressions in conditional probability expressions, we will be able to get this expression where we are replacing these joint probabilities using the conditional probabilities. Now after obtaining this expression, we can use the Bayes theorem in order to replace P of B divided by A2 and P of B divided by A3, P of B divided by A5 using P of A2 divided by B and P of A3 divided by B and P of A5 divided by B. So now let us write that expression also. B is equal to, here I can write P of A2 divided by B into P of B plus P of A3 divided by B into P of B plus P of A phi divided by B into P of A phi. But if we observe P of A, P of B, sorry, P of B. But if we observe, we are evaluating P of B and we are also getting the right side expression in terms of P of B. Once we are having the expression, once we are having, we have obtained the value of P of B, then there is, once we have obtained the value of P of B, then there is no use of this expression, because in order to evaluate this expression we need the value of P of B. Once we know the value of P of B, then this expression is itself not useful, because from this expression we are calculating P of B, which we have already calculated and which will be useful for us to calculate P of B from this expression. So this expression is usually not used, and usually it is of no use. In order to evaluate P of B, we have to use this expression itself, because in order to use this, the last expression, we need to first obtain P of B in order to use this expression, and in order to obtain this expression we need to calculate P of B. So either way it is not possible of this expression, it is not possible to use this expression in any practical purpose, and we are concerned with the above expression or this expression. We will be useful in order to calculate the probability of B. This is called the total probability. So these concepts will be applied further in understanding the binary symmetric channel and further concepts of probability. So these are the definitions of various definitions which will be useful in probability. So now let us let us pause this lecture here. In the next lecture we shall continue with analysis of the binary symmetric channel.